All right, guys, I'm back, and today I just want to talk about. So we've covered kind of the two main parts of 7-1 and 7-2 for Unit 7 Kinetics, discussing what the differential rate law, what it is, what reactant orders are, what they tell us, how we can determine reactant orders either using the data given to us, like different trials. We adjust the concentrations and we see how the rate gets affected by the changing concentration of a reactant. Uh, and then also, if given a mechanism, we've talked about reaction mechanisms and stuff. So today, this one, I just want to go through a few practice problems that are on some of the released exams and the practice exams. So if you've done a couple of the practice exams already, you might recognize these problems. And when you did them before, you probably had no idea what they were talking about. So hopefully now, if you've watched the two videos that have been posted on Unit 7 already, or maybe some of the College Board videos, um, now we look at these practice problems together, maybe they'll start making a little bit more sense to you. All right, so let's just dive into that. All right, so again, I'm just going to be scrolling through some practice exams or release material and just show you how it comes up. Now, also understand this isn't the only thing that shows up on the AP exam of kinetics. If you look at Unit 7, there is 7-3 and 7-4. We still have to talk about the integrated rate law and what that can tell us. But right now, we're just going to be focusing on the differential stuff and the reaction mechanism stuff. So I'm going to show you a couple problems based on that. All right. So let's look at that. All right. So let's look at number 48 here. So this, I'm not even going to look at the reaction, okay, or the question. I just want to look at the chart and just understand. And then we'll answer the question. And I don't think the question necessarily has to do with the chart, but let's look at this. If this is the data I'm given, I should be able to determine reactant orders based on this, right? So remember, don't automatically assume that X is first order and Y is second order, unless somewhere in this question they said the reaction happens in one step. If they told us the reaction happens in one step and that's the reaction mechanism, then yes, Y would have to be second order and X would have to be first order. Okay, but let's look at this reaction, right? And if you want to figure out the overall reaction order, you have to know what the orders are. So if we found out that X is first order and Y is also first order, the overall reaction order is second, right? But let's just look at the data. All right. So let's look at trial 1 and trial 2. Trial 1 and trial 2, we held Y constant and we doubled X. And notice what happened to the rate. It went from 8 to 32, right? I'm just kind of ignoring the scientific notation. So we doubled the concentration of X, but the rate quadrupled. So X is second order. X is second order. Okay? Then let's go to trial 2 and 3. We kept X constant and we doubled Y. And we doubled Y and the rate also doubled. So it's kind of goes against what we had up here, right? Y is first order and X is second order. And the coefficients don't show that. So the mechanism must be a lot different, okay, than what this reaction is showing. Okay, but based on that chart, we know that X is second order because when we double the concentration of X, the rate quadrupled. And we know Y is first order because when we double the concentration of Y, the rate only doubled. Okay, but now so that's how we would, and so if we wanted to write the rate equation, we would say rate equals K times the concentration of X squared times the concentration of Y. All right, but now let's go into this question. In order to determine the order of the reaction, the initial rate of formation is measured using different initial concentrations of X and Y. The results of the experiment are shown. In trial 2, which of the reactants would be consumed more rapidly and why? All right. This has nothing to do with the data here, and it has nothing to do with the initial concentrations. This is a stoichiometry question. You lose Y twice as fast as you lose X. It's a 1-to-2 ratio. So it would be D. Why? Because the rate of disappearance will be double that of X. So this question has nothing to do with, given this data, they're trying to fool you into picking X because you started with more X. Okay? But that doesn't matter. That doesn't matter. All that matters is the ratio. And for every 1X that is involved in this reaction, you lose 2Y. Okay? So again, that wasn't the question asked. We could answer a lot of questions given this information. We can do the math without a calculator. It's pretty easy. So, you can imagine a bunch of different questions given the same kind of data. But, the main thing here is just, what did the stoichiometric ratios tell us? And you could actually calculate the rate of disappearance of X for trial 2 is going to be the same as the rate of formation of XY2 because it's a 1-to-1 ratio. So you're gaining this the same rate as you're losing that. So the rate of disappearance of X is going to be 3.2 times 10 to the negative 2 in trial 2. But the rate of Y, the rate of disappearance of Y is going to be double this. The rate of disappearance of Y for trial 2 is going to be 6.4 times 10 to the negative 2 because you lose Y twice as fast as you gain the product, XY2. All right, so that's one question I just wanted to show you there. I think, let me see if there's anything else on this test. I think there might have been, maybe, hold on. No, not on this one. All right, so that's what I wanted to show you for that one. Let's go to here. All right, so here we have the same kind of data. We have different trials for a reaction of S8 and hydroxide. Sorry, my mouse is getting slow here. Let me see if I can. I'm going to pause and come back for you here in a second. 1 second. All right, it's not fixed, but we can work through it. All right. So we'll read the questions here in a second, but let's just see if we can determine anything. Trial 1 and trial 2, we kept hydroxide constant, and we tripled the S8 concentration. And notice that the rate kind of tripled here. It's not exact, and it's, if you were doing this experiment, if you're actually doing the experiment, you're never going to get perfect data like we did with that multiple choice question, where it was like this doubled and this also exactly doubled. But it's pretty close. Like this is close to 0.7, and then 0.7 times 3 would be 2.1. So we tripled the concentration, and the rate also tripled, so we know S8 is first order. All right. And then I guess here we have to know, like, we kept this concentration the same, and the rate doubled. So we have to know some information about the order of hydroxide to figure out what this concentration would be. All right, so E1, we determined the reaction with the order of the reaction with respect to S8. So that's just asking us the reactant order of S8. And we just found out it was first order. Why? Because when we tripled the concentration of S8 and held the hydroxide constant, the rate also tripled. That's a first order reactant, right? If the rate stayed the same, then we know S8 is 0 order. If the rate got multiplied by 9, which would be tripled squared, right? 3 squared, then we would know S8 is second order. But because we tripled the concentration of S8 and the rate also tripled, we know it's first order. Okay. So it says determine the value of hydroxide that was used in trial 3, considering the reaction is first order with respect to hydroxide. So they just told us hydroxide's first order. They just told us hydroxide's first order, okay? And so since we kept the S8 constant, and we and the rate doubled. It didn't double because of what we did to S8. It must have doubled because of what we did to hydroxide. So this would be 0.02. So the answer here would be 0.02. And it's because between trial 2 and trial 3, we kept the concentration of S8 constant, which would not affect the rate at all. The rate between trial 2 and 3 doubled. So because hydroxide's first order, that means the concentration of hydroxide must have been doubled. So the answer here would be 0.0200 moles per liter or molar. Okay, does that make sense? Okay. Okay. So this is just asking why the student did trial 4, but it was the same concentrations as trial 1, but the rate was much slower than this one, but they noticed that the temperature in the room was colder. So what would happen? So because the particles will be moving slower, so they're not going to collide as much, so you're not going to get as many collisions in the same amount of time. And then also the collisions are going to have lower energy because they're not moving as fast. So you have less collisions, and less of those collisions will have enough activation energy. So if we're looking at part F there, okay. All right, so those are the kind of the two that I wanted to show you based on. Let me see if I can find something else here. Yeah, I think. No, okay, I don't want to talk about that yet. All right, so let's go to some mechanism practice problems. Okay. All right, so here's a question. Whoops, where they show us a reaction, and they give us the rate law, and then they tell us here that the reaction occurs in a single step. That means this is the reaction mechanism. So that means NO shows up once and NO3 shows up once, so they're each first order. So that makes sense. So it says the scientist correctly calculates the rate of collisions between NO and NO3 that have sufficient energy, so enough activation energy, but the observed rate of reaction is only a small fraction of those collisions. So even though the number of collisions that have enough energy are high, the reaction's happening at a slower rate, and it's because, remember, the particles have to have the right orientation. So the answer here would be why is it still slow, or slower than what the number of collisions with enough energy have? Because not all the collisions with enough energy will have the right orientation, right? So that would be answer B there. All right. So that really didn't have anything to do with reaction mechanism, but I wanted to show you how if you have a single step, that means that mechanism is, or that reaction is the mechanism. And then I think there's another mechanism question here, if it's the right one. No, that's not the one I wanted. Let's see, no. Sorry, bear with me here. I'll pause it until I can find the next one. All right, so here is another reaction, or here's a mechanism. Okay, so if we wanted to, we could add this reaction up. So let's just look at this reaction mechanism here and identify the intermediate if we have one. So the intermediate in this mechanism would be ClO. All right, so that's what chlorine monoxide. So ClO, they cancel out this way, so that would be our intermediate. And this mechanism is a catalyzed mechanism because we do have a catalyst, and that's the chlorine atom here. Chlorine cancels out this way. Chlorine gets consumed and then produced. So chlorine is a catalyst, and ClO is a intermediate. So again, this is a catalyzed mechanism. The question here is, here's a proposed mechanism for the destruction of ozone. Which of the following is evidence that the mechanism is occurring? And I'm gonna guess it's A, because it's saying the presence of chlorine increases the rate of the overall reaction, and that's what a catalyst does. And chlorine is a catalyst in the mechanism, so that's what they're saying here. Yeah, all right. So that's all that one. Let me find some more practice ones, and I'll be right back. All right, this is a practice free response. They give us a mechanism. So the rate determining step is the slow one. So we know the first step of the mechanism here is that we can check on a couple things. Does this add up to the overall reaction? And the answer is yes. Do we have a catalyst? No, we don't have anything that cancels out on this diagonal, but we do have an intermediate. The intermediate is F, right? So F's an intermediate, and this is an uncatalyzed reaction, all right? And so what I want us to read in this question is, I want to go down here, and based on this mechanism, which would be the correct rate law? So because this was the rate determining step, remember we only look at that step and anything before it, but since there's nothing before it, we'll only look at this step. And fluorine shows up once, so fluorine, F2, is a first order reactant, and NO2 shows up once, and so that is first order. So this would have to be the right rate equation because it shows fluorine and NO2 as both first order. This would be the right rate equation here if this were the rate determining step, the second step, because it would show NO2 twice and fluorine only once. All right, but because the first step was the rate determining step, boom, I know that that is my correct rate equation. All right. So I just wanted to show you a couple of those questions. So you should be able to answer the rest of the questions. It's about, collision theory, what has to happen for a reaction to occur. You have to have the right orientation of particles, and you have to have the right activation energy, that kind of thing. I think there's one more question I want to find. I know I had it. Let me go find it. I got to figure out what test it showed up on. So just give me 1 second. Okay, so this isn't the one I wanted to show you, but it is another good example of reaction mechanism question. So here's our overall reaction. Here's the reaction mechanism. So this is the slow step, and this is the fast step. So our first step is the rate determining step. It shows NO2 showing up twice. Look at that, 2 times. So it's second order. And then that means the CO, the carbon monoxide, since it's not in the rate determining step or previous steps, that means CO is 0 order. So B would be the right answer. This would be the right rate equation. If it were, if this were the slow step, if the second step was the rate determining step, the right rate equation is not up here. It would show NO2 as being second order and CO as being first order, but that's not one of the choices here. So we don't have a catalyst, but we do have an intermediate, the NO3 molecule. There's the intermediate, okay? All right, so I think that's good. I just wanted to give you a little bit of practice stuff. So, oh man, I can see the video is kind of jerky, and I hope the audio isn't either. Let me. All right, so I hope that didn't affect the video. I'll double check it, and if it did, then maybe I'll try to redo this video tomorrow. It's spring break. What are we gonna do? All right. I won't know until I stop the video. So, all right. Sorry about that if it's all herky jerky. All right. At least the first video worked out okay today. All right. Have a good one.